The last topic in Chapter 7 is cables, and I'm just going to skim over it. You do have two homework problems that I'm not collecting, and it won't be on the final. But it's something you should see, and if you ever have these type of problems, you can come back to these videos or find it in the book. Before we solve some problems, let's just do some counting. This cable, this rope that you're hanging from A to E, is hanging 3 loads. So you have this 4 kilonewton load there, a 15 kilonewton load, and a 3 kilonewton load. And when you put 3 loads in between the span, what that does is it makes 4 segments. 3 loads will make 4 segments. 4 loads would make 5 segments, and etc. Now let's count unknowns and equations. There are 4 reactions that are unknown. There are 3 drop lengths. We want to know how much the cable sags at each of the loads. So there's 3 of those. Okay. And there are 5 joints. If there are 4 segments, there are 5 joints. 1, 2, 3, 4, 5. So the total number of unknowns are 4 reactions, 3 drops, and 4 tensions. There's a tension in each segment of the rope for a total of 11 unknowns. And the total equations at each node, you get 2 equations. Some fx is 0 and some fy is 0. And so you'll end up with 10 equations. You need one more equation, and this is always the case because every time you add another load, you get another segment, and it'll always be one more unknown than equation. So just believe me that always is the case, that you always need one more equation. Typically, in a real problem, the extra equation is I have 35 meters of rope or something like that. And you know that the total cable length is given. You know how much cable that you have when you're going to tie this all up. There's a problem like this in the book where the total length is given and you have to solve for everything. It's extremely complicated. You have 11 equations and 11 unknowns, and it's really tough. It's a real problem, but it's also very difficult. Here's a little more solvable problem. You're saying, oh, I want point C to only sag 12 meters, and I'll shorten or lengthen the rope to make that equal exactly 12 meters. That's not a real problem, but this one is much more solvable, and we'll walk through the solution for this one. Here's an outline for the solution. The first thing we're going to do is solve for AY and EY, and then we're going to observe that AX equals minus EX. And then finally, we're going to use the method of sections to solve for the tension in BC and the tension in CD. And then we're going to work our way towards the end and get the tension in the other 2 ropes. Here's the problem statement. They're asking us to get the tension in each segment of the cable. This is not a pulley, so the tension is not the same in all the segments. In fact, they're different. Doing the statics, summing forces in x equals 0 gives that minus ax plus ex equals 0. They are equal and opposite, so you have ax going to the left, ex going to the right. Summing moments about E gives us that ay is 12 kilonewtons, and then summing the forces in the y, or you could actually sum forces about A. Either way, sum moments about A. You get that EY is 10 kilonewtons. Next, taking the method of sections, cutting through the rope that goes from B to C, you get this free body diagram here. And using sum moments about C, you get EX, AX, which is also EX. Then summing moments in the X direction and the Y direction lets you solve for the angle and the tension. It's actually a pretty complicated problem to solve, but you can do that. Now we're just going to proceed using the method of joints and go joint to joint, and you end up getting the angle and the tension in AB, and the angle and the tension in CD, and finally you get the angle and the tension in ED. This is a complicated problem. You can look through all the details to see how it works, but this is how you do these types of problems. And if you're really interested, you can also get the equation of a cable that's sagging between two supports. So you have a cable that's going like this, and it has a distributed load on it. And if you want, you can read the book on how this works out. The equation for this sagged curve is given by this integral, and if you put in just the weight of the cable itself, when you do those integrals, you end up with this hyperbolic cosine that solves for the equation y. So this curve here is given by cosh, hyperbolic cosine, and the maximum deflection here in the middle is given by this equation here. You would need to know this sort of thing if you're building a suspension bridge, or you're building like a wooden bridge across a canyon and you're just stretching a cable across there. So that's just a very, very brief overview of how to handle cables. If you really need to do this in the future, let's say you design suspension bridges, you'll look at this in much more detail.